Hello everyone, this is Francisco. Welcome to another tutorial on language design in SEMA. So on the previous tutorial we looked at how to create token definitions with regular expressions in JavaScript for our Lexer definition in the grammar editor. So that allowed us or allowed the parser to understand what are the words of the language or the vocabulary that it needs to recognize. Um, and these tokens are used in the grammar rules, in the grammar definition. So the grammar rules, they define what is the logic that tokens should be recognized. Um, so in this tutorial, we're going to look at, we're continuing to learning more about regular expressions, but we're going to focus more on our grammar rules. And so on the previous, we managed to get to a point in which we defined a language that is able to understand three words. So it's a three token language that plays three samples. On the previous tutorial, we had three rules for our statement, for the statement of the language, and each of those rules derived in a specific symbol. So here we're introducing a very small improvement, which is using this symbol that enables us to make many derivations to a single rule, and it will have this form. So instead of having three rules for statement, now we can have a more readable and organized grammar with one rule with three derivations with the R symbol. So there's something else that we need to know, which is what is this bit of code that comes with each rule. So this code block, which is delimited by curly bracket, percentage, curly bracket, is what's called a semantic action. And this is something that our parser generator can use to execute specific actions whilst he's recognizing tokens. So for each successful token recognition in our grammar, and for the backtracking that happens in the rules that led to a successful recognition, the semantic action is going to be executed. And in a semantic action, we have nothing more than a function written in JavaScript that has some logic. So for instance, in this piece of code here, in this semantic action, we have an arrow function in JavaScript which basically returns a list with one object that has this nested structure in JSON. And this is the intermediate language that we've created in SAMA to help building an abstract syntax tree that will then be used for the code generation that our signal engine needs. And you can know more about this intermediate language in the documentation right here at SAMA intermediate language, where all the main types of SAMA are defined and how they're mapped into specific objects that enable you to build that nested structure that we have. So you can go through all of them and see how they how we need to define them in a way that makes sense to build an abstract syntax tree. So we're going to see how that happens for our simple language. So if we want to play a sample, basically we're creating a process, a signal processor process that has uh, other signal processor processes embedded. So for instance, if we want to play a sample, we're going to create this little block here that has a function that plays back a loop with a specific sample. Here's the name of the sample with a specific variable that, in the case of a loop function, determines what's the speed of playback of the sample. And then this is wrapped by a function that just outputs the sound or the audio of the sample. And so if you compare that with the other derivation that we have, the only difference that we'll find is specifically on the name of the sample. So the code, the structure for the rest is pretty much the same. Now we want to add another feature to our language, and we're going to add the possibility of playing an oscillator. So we already have 3 samples, so now we want to play a sawtooth oscillator. So we're going to have our language recognize the word saw, and for that we're creating a new regular expression associated to the token definition. And now we're going to add the piece of the block with the nested structure that we need for saw. So we're adding that to the statement. And if you compare what's the difference between playing a sample and playing an oscillator, the difference is pretty much 3. So the function is saw, because our signal engine knows that he has to play how to play a sawtooth wave. The parameters will be the frequency of the oscillator, and there is no need for a string with a name. So let's try this out. So if I turn audio on, I can still play click, but now I can play a sawtooth waveform. Okay, cool. Now this value here of the sawtooth oscillator is fixed, so if I want to change it, I need to write our own grammar, which is not a really good thing. So I want to make that part of our language. I want to make the frequency of the oscillator part of our language. So I'm going to create a new symbol in our rule, which I'm going to grab with this index. So two. So this is how we grab the value of the specific symbol in the right hand side of the rule. So if this would be D0, the space also counts, so it's D1, this is D2, And now we need to know how to recognize a number. And for that, we have to define a new token and add a regular expression for the number. Now, we already have this here. I'm just going to quickly grab it. And let's see if we have now oscillators, a sawtooth oscillator with a frequency. Yeah. Okay. Cool. Now, so we just added a number to our language. So let's add, instead of having a fixed oscillator function, let's make that variable. And I'm going to use another regular expression that reads letters from A to Z that occur once or more with the plus sign. And I'm going to change saw to OSC, so to make it more generic. And I'm going to replace that here. So OSC. Okay, so now that we have the capability of reading a new function from a string description, I'm going to grab it here as well. So let's try this out. Saw, triangle. Oh, there you go. Cool. Sine wave. Square. Ooh. Impulse. Nice. Okay, so that wraps up our grammar explorations. We have now a slightly more powerful language that plays 3 samples and a bunch of oscillators with variable frequency. And in the next tutorial, we're going to see how to make our language even more powerful. Stay tuned.